So welcome, Pranavji. Please take over.
Okay, so let me start. So today's talk is science befriends Vedanta. So, so what I'll be talking about in this talk is I'll take one physics concept and I'll look at how I won't be talking much on the physics part of it, but I'll take some examples of the concepts in physics, and I'll tell you how deep one can actually investigate into these topics. And and what I want to convey is that, when somebody takes up a topic in science, let's say, when somebody takes up a topic, and when somebody digs deep enough, when somebody investigates deep enough, uh, I want to show you how the thought process of digging deep is equivalent to the thought process of a Vedanta, a person along the Vedanta part. So this is the parallel that I want to draw, and I'll be taking up an example, a small example in the field of physics, um, to convey this message. And that's why I've titled it Science Befriends Vedanta, because the thought process is very similar. Yeah.
Yes, bro.
So, uh, so to begin with, if you look at the branch of physics, we have, you can divide the branch of physics as, so we have these two theories, and these two theories, these two models of the universe are the most successful models that we have right now. So one is general relativity, the other one is called as quantum field theory. So any physics that you see, anything that you observe right now, you can put into one of these two baskets. And these two are the most successful theories that we have had right now. So general relativity deals with something called as space and time, and quantum field theory is mainly dealing with matter. So these two are the most successful theories of physics, and these are the two pillars of physics, you can say. And so today I'll be talking about general relativity. I won't go into the details, so you don't have to worry that the talk is going to be very pedantic, but it's not going to be. Uh, yeah, so let's quickly, I'll just quickly show what is this field and how the questions come up, and how these questions are very, very nice, and they're also counterintuitive. So yeah, so let's dig into it. So if you look at general relativity, there are two ingredients, like I said before. One is space, the other is time. Now these are concepts that we are very familiar with. We know what space is. So, you know, everything that we see around our world occupies some space. So you say my height is 170 centimeters. You say box dimension is 30 centimeter by 30 centimeter by 30 centimeter. So you see anything that you see around occupies certain positions, and this is nothing but space. So there is space around us, there is so much there's so much happening, and everything occupies some space. And we are very familiar with the concept of time. So everybody has clocks nowadays, everybody has follows time through on the smartphones, and everybody is very familiar with the concept of time. But if you dig deep and enough into what space is and what time is, you'll actually end up with very, very contrasting, very, very confusing, very, very non-intuitive pictures of what space is and what time is. And this is the flavor that I'm going to bring about in the talk today. So first off, a little bit of history, because who doesn't? I mean, everybody likes history. So, so people have always been curious. So they want to know why things work, how things work, and so on. So they see things moving, and so they want to quantify this change. Things are moving around. I'm waving my hand. So you want to see how exactly this hand is moving. A train is moving. You want to see how the train moves, how fast the train moves, what is the weight of the train, and so on and so forth. So people are always curious about these kinds of change. So people have always tried to formulate models of what their understanding is. So this is essentially the branch of physics. It's essentially trying to understand something of the nature, trying to some explain some observations that you have. So anything that you see that is moving around in space, and it's moving around in time, and people have always wanted to quantify this. People always want to know how things are moving in space and how things are moving in time, and what is the space and what is this time. So the history of quantifying this has always been was always there, and it started with early Greek people, Aristotle and so on and so forth. They proposed some models of universe, and then Newton came and said, no, this is wrong. uh, Things move in a different way, and so on and so forth. So people have always been curious about these kind of changes. So anything that you experience is a consequence of a change in space and in time. So when I move my hand, the hand is moving from this position to this position. So it's a change in space. And there was some time gap between this, when the hand was here and when the hand was here. So there's a change in time as well. So any actions that you have, any dynamics, any changes that you capture, you try to capture, is a change in space and time. Now, for the longest of time in history, people always thought the space and time were independent things. That space doesn't really depend on time. It doesn't matter. So I can keep my hand here for as long as the time I want without changing space. And similarly, you can always see something. You can always say that time doesn't flow backwards. So time is always going forwards, and so time is decoupled from space in that regard. So for the longest time, the thought process within the community was that space and time are completely two different things, and any motion, any dynamics that you see is a change in space and a change in time. And now there is this person called Albert Einstein, and he comes in and he says, he comes in and he drops this amazing theory, amazing work, and he says space and time are relative. He says space and time are not different. They are to be treated as on similar grounds. So I'm going to explain, I'm going to talk about this for a few more slides on how exactly this works. So trying to capture the non-intuitiveness of space and the non-intuitiveness of time. We are all aware that we are all aware of the simple fact that space and time are separate, because I can move my hands around and it feels like I'm moving in space, and I can move my hand around slowly, fastly, and so on and so forth. And so things seem to be very, very decoupled. Time doesn't depend on space, and space doesn't depend on time. So uh, so Einstein brought this theory of relativity, where space and time uh, space and time are thought to be are thought to be are brought to the same platform, and they are not as decoupled as we thought they were. They are in fact very closely related. And one of the simple examples is this cartoon that I'm showing here. So let's say there are two scenarios. One where there's a person, and the person is just sitting, and the person is observing, let's say, a rod, and the person is also keeping track of time. So let's say this is the hand, so he's keeping track of what the length of the hand is, and he's also keeping track of the time, and the time of how long he's observing, let's say. So now there is this rocket that's going at a really, so let's say this is a cartoon rocket, so it's going really fast, so fast that we haven't been able to achieve these speeds in real world. So it's going very fast, and there is the same rod that I have placed, and there is the same watch that is keeping track of time in the rocket as well. Now it turns out, if a person is observing this rod, and if there's a person who is actually observe the rocket, and if you see what the length of the rod is, for the person outside, the length of the rod is, let's say, some length, I don't know, 10 meters or something. For the now when the rod is actually traveling at a much higher speed, which is the case over here, that the rod is in the rocket, the rod actually shrinks. So space actually shrinks as you go faster and faster. And what happens with time is time slows down. So if a person measured 15 minutes outside, the person for relative to the person who's going in the spaceship, who's going in the rocket, for that person time there has been only 10 minutes that has passed instead of 15. So time actually slows down as you move faster, and space actually shrinks as you move faster. So this is this theory of relativity. So another example that I want to show is this. So c is called as the speed of sound, and it's the measure of how fast you go. So essentially, when so there's a basketball over here. You're moving with no speed, then the basketball maintains its shape, and as you approach faster and faster speeds, you can kind of see how the basketball is shrinking and shrinking. So this is how the universe works. And over here, there's another example. This is a very famous example that people were stumped for a long time. It's called, so there are these tiny particles called muons, and these particles travel very fast. They just keep buzzing around. And for the particle, it takes only 2 seconds to change into another particle. But since it's moving so fast, when we look at the particle, it looks like it's taken 100 seconds. So if you were to shrink yourself and go into the particle and see from the particle's perspective, it's only 2 seconds. But if I go back and observe the particle from the laboratory, then it takes 100 seconds. So this is how the universe works. It's very non-intuitive in this regard. So it's like saying, so when I'm here and I see Usain Bolt running, so I measure some time, and then Usain Bolt measures another time, and then Usain Bolt says I ran in 9 seconds, but that same 9 seconds for me is like 10 seconds. It's not so huge. That's why we still have clocks that work. You need to go to really large speeds in order to see these effects. But nonetheless, these effects are always there. So with this one instant notion, Einstein just shattered the concept of what space and time is. So space is relative, and time is also relative. So it all depends on how fast you move. So there is nothing called as fixed absolute space. There's nothing called as fixed or absolute time. Everything has become relative now. with respect to what is the main question now. So if you say I have measured 5 seconds, with respect to what is a question that has to come up. If I say I measured a box whose length is 30 centimeters, with respect to what is the question that should come up. So everything has become relative now. There's nothing that is absolute. So initially people always thought space and time were such fundamental concepts, and they have to be absolute. The time that I measure has to be the same time that you have. The space that I measure has to be the same space that you have. And here comes this amazing, beautiful insight into the reality of nature, and it has brought about this completely different approach where space and time are entirely relative concepts. So it's always with respect to something. So things can get really, really crazy in the universe actually. So there are these huge objects in the universe called as black holes. So if they're really, really huge, they're inconceivably huge and massive. So if you think about the earth that we have, you can fill more than 1,000 you can fill more than 1,000 earths into one sun alone. So the sun is so huge. Now imagine filling hundreds of suns into a very, very tiny place. So that is how massive these things are. These things called black holes. It's so huge that even light can't escape from this. So very, very interesting things of space and time happens close to a black hole. So in fact, there's something called as an event horizon, which is the point of no return for light. So if you go past the event horizon and go into the black hole, light cannot escape from the black hole. That's why it's called a black hole, because we don't know what happens there. Even light cannot escape. So what happens right at that point of no return is space and time, they kind of flip. So what feels as space is actually time, and what feels like time is actually space. So for a person who is falling into a black hole, he feels a normal time because for him everything is at rest. But for an observer outside, which is the case where you are seeing a person falling into a black hole, as time moves forward for that person, this person moves in space instead. So this is how weird things can get. I'm not getting into the details of this, but imagine a scenario where time and space just completely flips. So it looks like things are moving forward in time, but you're actually moving forward in space. And it looks like you're moving around in space, but actually you're moving in time. So things can get really, really weird in this in the very in this thing called as event horizon of the black hole. So there are these amazingly non-intuitive objects that are present in our universe. And one often thinks then one often starts to think, what are these consequences of such things, because now we have entered from a regime of our comfort, which is where time and space is fixed. We have gone from that regime to some completely unknown territory where things are extremely non-intuitive in this regard, where space doesn't follow the way it has to be, time doesn't follow the way it has to be. So one way to think about this is everything is relative now. So as a kid, so how to deal with this non-intuitiveness? So as a kid, kids are actually the most efficient in grasping non-intuitiveness, because what is non-intuitive is because we have had so much training in our life to understand that something has become intuitive, and then if there is something that doesn't obey those rules, it becomes extremely non-intuitive. But for a kid, it takes things for granted. It sees as it is, and so everything is just intuitive for the kid. So one simple example I want to give is this kid, and let's say there's a parent along with the kid who's traveling in the train. So when the kid travels in the train, for the kid is sitting in the train, so the kid is not moving. What is moving is the trees outside the train. So as the train moves, the kid sees that that the trees are going back, and then the kid says, "Oh, look, the trees are moving, the trees are going back." And then immediately the parent comes in and starts correcting the kid, saying that the tree is not moving, the train is moving, and that is why the tree is moving. It seems to move. But in fact, if you look at things, every it's that is not the case. Everything is relative. So with respect to the kid is in fact sitting, and for with respect to the kid, the tree is in fact moving. So if I were to say and go and talk to the parent and say the tree is in fact moving, it's a very non-intuitive thing for him, because he has seen the tree is always at rest, and he has seen the train move, and he sits inside the train and he knows that the train is moving, and so he is moving, and so the tree is not moving, he is moving. But if we need to change this perspective and define what is movement. And in fact, for the kid is in fact at rest, because the kid is not moving. The kid is in fact at rest, and the tree is in fact moving. So the train is moving is also true, the tree is moving is also true. The question is with respect to what. So this understanding this understanding of with respect to what is something moving is the new perspective that is brought about in this new concepts of physics. So so something that we thought were absolute, where the tree doesn't move and the train moves, is not really true. The tree is also moving, the train is also moving. The question is with respect to what. So absolutes have now changed in physics, and and absolutes have become relative. So space, so whenever you talk about something, you say space with respect to what, time with respect to what, and so on and so forth. So this is one very fundamental thought process that comes up in this field of physics, where things have become where we have understood that things have become relative. Absolutes have taken a backseat. Uh, so I'll go into a bit more detail here. So if space and time are relative, so then the next obvious question comes: is there something that is more fundamental? Is there something that is more absolute that actually governs the dynamics of this space and time? So one way to think about this is to think of space and time as this fabric, the sheet, and energy as this thing that warps the sheet. So you see there's a rock that is placed over here. So as soon as you place a rock over here, the sheet bends around, right? So essentially this rock is nothing. Think of this rock as nothing but energy. So what really is governing this motions of space and time is actually the energy around, is actually we call it as mass energy. So it's actually this energy that governs these equations of space and time. So one can again ask if there is something more fundamental to this energy, and this is where physics research has headed to right now, trying to go behind this fundamental things. So but the important point what I want to convey over here is that, as you dig deeper, as you start doing more and more research into things, you discover that things have become more and more relative, and there is this quest of uh, of trying to achieve the most fundamental things the most fundamental explanation to things. So this is what happens when you start digging deeper and deeper. So you eventually end up with these kind of questions which are deeply related to philosophy. So you end up with questions like, is there a concept of, and this is in fact a very nice, very sought after question. Is there a concept of space and time if everything is still? So so if there is no energy, if there is nothing, is there a concept of space and time? Uh, so these are some of the very fundamental questions that pop up. What is space? What is time? Uh, is there space and time when things are still? And you can see that if you have some background in Vedanta, uh, you can see that these are extremely relevant questions in Vedanta as well. So what happens is, as you keep digging deeper and deeper into the nature of universe, you end up with these. You always end up. You inevitably end up with these kind of extremely fundamental questions. So I just want to give one simple example of one not an example, but an analogy of how really science works. So everyone begins with some preconceived notion. So there is this scientist over here. So he has this preconceived notion. He has learned some things from high school, from graduate college, and so on. And he has some preconceived notions. Like there is so like for example, for this person, he knows that there's something called as gold, and he knows that gold is precious. So this person is digging in order to find some gold. So the next stage is, you persevere, and if you persevere enough, surely you'll hit some gold. And this person has persevered. He has done some research in life, and he has found some gold. He has found some new work. He's found some new understandings of the universe. He's found some. Uh, he's gotten some gold. But truly experienced veterans. So these guys have been digging for a long time on the same topic, general relativity. On that same topic, all of these people have done PhDs. They've dug deep enough, and they've even got Nobel prizes. And then when they dig deep enough, obviously they'll find so much stuff. But what they also understand is there is so much gold, and there's so much more. I keep digging and I keep getting some things out. That's the nature of the universe. So you keep digging on something, and you always end up finding something new. And you keep digging, you find there's so much gold, and you start questioning those fundamental things that started this whole journey itself. So you start questioning, now so much gold, what to do with this? What exactly is this gold? Why exactly did I start? Why exactly did I search for gold to begin with? So this is how, if you speak to like people who have done a lot of research, who have been in the field for like 40-50 years, if you go talk to them, they're extremely slow in replying. They're very measured in replying to some to some questions that you think are very easy to answer, because they've found so much things that they're not sure about any of it anymore. So so this is how I feel. This analogy is how I feel science works. So you dig so much, you extract so much things, that finally you end up with these you finally end up with these mundane questions. So you initially start off by looking for something special. You think that there's something special, and you look out for the something special. Then you in fact find that something special. You are very happy. Then you keep looking, and you found out that something that was special is not actually so special. And so you go back to those very mundane questions that no one ever asks, because it's all thought to be, it's granted that those questions have always had answers. But this time, when you go back to those questions, those very fundamental questions, they're not so mundane anymore, because you have this huge wealth that you have analyzed, and you have this huge wealth to know that these questions are deep, and these fundamental questions are not mundane anymore. So this is the journey of a scientist, and you see that this is also the progression in Vedanta. So everybody starts off their search trying to look for something special, and then you hit some small special things in life, and you hold on to it dearly because you think it's special. But then you take another leap forward and you start digging more, and you find out that and then you find out that what was special is not so special anymore. But what is special are those small questions that you never thought to ask. Those small questions that you thought were obvious, but it's not so obvious. So this is how a deep dive into science is nothing but a deep dive into Vedanta, because those tiny questions that you forgot to ask, but now that are very relevant, I feel is the same kind of questions that you ask if you are in science or if you are in Vedanta. So I just want to conclude by this statement. So a deep dive into nature is nothing but a deep dive into Vedanta, because all that is there is nature, and we are just trying to understand aspects of this. Thank you.
Oh, wonderful, wonderful, Pranav.
Yeah, wonderful. Yeah. I can see the gold and the happiness similar. Yeah. Yeah. Happiness is most uncommon in the beginning and the most common and the only thing that is there finally. That's good. Fantastic. Fantastic talk, Pranav. Yes, Prabhuji.
Thank you.
Yeah, this black hole
Yes.
where everything disappears. Does anything
Yes.
reappear on black hole?
So there are some.
Big Bang is a singularity of Big Bang is a reappearance of what was there in black hole appearing?
So there are some theories, but there are many theories. So everybody has a theory nowadays on what things are, but there is no way to know what the reality is, because there is no way to know what exactly happens inside a black hole. So there are some theories. So there's something called as a white hole, which is exactly the opposite of black hole. So black hole, think of it as absorbs everything.
Yeah.
And white hole does the exact opposite. It pushes
pushes
matter.
out.
Yes, pushes out everything possible.
Yeah.
So there are analogies like this, and then there's something called as a wormhole, which connects two black holes, and this allows time travel possible. And so there are all of these different analogies, but what we know for certain is that a black hole is actually what we call as so it's a point of so it's called as a singularity. But when physicists talk about singularities, what we actually mean is that all our theories fail at that point.
Oh, okay.
There is no way there. That's why it's called a singularity. We have infinities when we do.
Yeah.
So the language we physicists express universe is in terms of mathematics.
Okay.
So our mathematical models fail at that point.
Okay.
That's why it's called a singularity. So a black hole is actually a singularity in time. It's not in space.
Singularity in time. Okay.
Yes. So that's why. Yes. So it's a singularity in time. So time goes to infinity there. Time diverges. So it's
Okay.
a singularity in time. It's not a singularity in space. But the space and time, like I said, is so warped around over there. What is space becomes time, what and so on. That's why it looks like it's a singularity in space, but it's actually a singularity in time.
Isn't it a
Now
singularity
on
in
this,
space and time?
Sorry?
It's a singularity in space and time fabric.
Yes, so in space and so think of it like, so I showed you how that fabric curves around, right? So think of it like an infinite well at exactly that point. So
Mm.
that's how the space and time. So that's how space and time is warped around. That's how we express singularities. It's gone to infinity.
are we living inside a black hole or outside a black hole? Are we?
Or so Guruji, I want to right now. I want to take science and spirituality out.
don't, don't ask about the experiencer here. It's all about experience. The moment you bring in experiencer, then it is Vedanta.
All I've said is science will lead you to questions. I never told science will give you answers.
Super. Very clear. That is true.
So what they say is that on the surface of the black hole,
Hmm.
the holographic, whatever is swallowed by the black hole remains in the form of holographic form. Is it true?
So okay, so this is holography has a very different meaning in physics. I don't know much about this,
Okay.
but what it actually means is that so what it actually means is, so the way holography works in in real life is that you have a 2D system, you have a 2D image, and then you
Right.
shine light onto it and you project it and you get a 3D object out.
Correct.
So that's how holography works. So the
Right.
analogy of holography over there is that, so space and time is actually 3 dimensions of space and 1 dimension of time. So totally it's 4 dimensions. So holography over there is an equivalence. So the equivalence is that the entire 3 dimensions of space and 1 dimension of time actually lives just at the edge, in 2 dimensions of space and 1 dimension of time. So whatever goes on in the bulk, you can describe by just looking at what happens on the edge. So that's the holography. Just like how when you shine light onto a 2D material, but you get a 3D object out, because all the information of the 3D object is stored in the 2D material surface itself. Similarly, what happens in the entire bulk of it is actually described just what happens at the boundary.
Boundary.
So just by looking at the boundary, I can know what can happen in the bulk. So this is the holography principle that we have. Things are a bit more complicated than that, because the holography principle for us is actually not 3 dimensions of space, it's 4 dimensions of space. Something that we can't even imagine now. Yes, so that's the holography principle.
Okay.
I don't know much about this because I don't do research on this.
Okay. Wonderful, Pranav. Now, where does this quantum theory fit into this whole system?
Right.
Quantum
So
theory is quantum theory is at of course at the macroscopic level we are speaking, macro level we are speaking of the black holes and all. At the quantum
yes.
level, are quantum black holes are they?
So you can have analogs, yes. So in my system, you can actually have a lot of analogs. So in fact, there's been this new discovery where they have an analogy of this wormhole that I was talking about. But in systems that I deal with, when you put a lot of electrons in it, it turns out these electrons behave as though they are in a wormhole. They are like in a wormhole, but it's not.
Okay.
It's not an actual black hole, but it behaves exactly the way it is. So there are these all sorts of analogies that come up. But I want to go back to your original question, where quantum field theory fits into this. So, if you looked at my slide, in the second slide, I said there are two successful theories. One is the relativity theory. The other is quantum field theory. So, a huge number of people are actually working in order to reconcile these two theories. So these two are the most successful theories, but when you try to put them together, everything just fails. Everything just collapses.
Right.
So this new like string theory and there are so many other theories, and all of these are trying to marry these two concepts. So this is what people have been working because one, it works brilliantly at macro levels, and the other one works brilliantly at micro levels. But if you try to put quantum theory of gravity, things start to fail.
Theory of everything
So,
is not there.
Yes. So theory of everything is essentially merging gravity with quantum field theory.
Okay.
Yes.
Okay.
So that is what it is. So yeah. So this. So we have these analogies. All these. In fact, the analogy of what a quantum aspect of gravity is not realized outside in a black hole or in reality, but it's actually seen in it's actually predicted to exist in systems that I do, where you take a huge number of electrons and they behave as though it is like that. So that is
Okay.
how it is. Yes.
Yeah, Pranav, thanks a lot. Wonderful analogy, wonderful this thing. Well, ultimately, we are left with only questions, no answers.
Yes. Answers you will give, Guruji.
Answers Raman Maharshi gives. Sumaniro. Sit quiet. Whatever question, the moment you open your mouth, only questions are there. And the moment you find the answer, he will not be speaking.
Yes. No questions will be there.
No. Okay. Thanks, Pranav.
Thank you.
Thanks. And is there any question from others on the Zoom or Rita ji, Supriya ji, and then I have Pratibha ji, Jagadish. Anyone have any questions for Pranav? Okay. So I think your talk is so deep that people take some time to even think about the questions, Pranav, but it's a wonderful talk. In the end, one of the things that I was wondering is there a reference frame at all? Because originally we see that even for relativity, there is a reference for two moving objects at different speeds. From outside also there is a reference. But if you extend it further, in black hole, there is no reference. I mean, each one, both ends of the wormhole have their own references to their own signs also. But is the reference or absolute? How is it defined? Or is it defined at all, or they don't want to define it at all?
So I'll just go back to the train and tree analogy. So for you, so let's say, so in this case, the tree is the black hole and you are in the train. So you are observing some things happening over there, and that is that is how it is for you. So it's with respect to you. And what happens near the tree is another thing with respect to what happens with respect. If you are standing next to a tree, then the train is moving. So with respect to the train is moving. With respect to the train, the tree is moving. So reference frame is just depend. So there are so physics. So these quantities, space, and so there's something called as space and there's something called as time, which depend on reference frames. But there are some quantities that you can define which are constant irrespective of the reference frame as well. So
Correct.
there's something
Exactly.
called as proper time, and there's something called as proper space, which you can define,
Correct. Correct.
which are constants. So these don't
Yes.
depend on reference frames.
Correct. So
Yeah.
that's how they, in fact, the mathematics today can find out what is the measurement from a given reference frame and from another reference frame, from a third frame also. That I
No,
can
it's
understand.
not a third frame. It's not a third frame. There are no third frames. So it's all just different frames, and things are just relative to each other.
Correct.
So there is physics that is equally applicable in both frames. The physics is the same. It's just that variables, quantities are different. So
Correct.
time
So,
that I measure and time that you measure are different, but there is physics that governs how this time works, and there is physics that governs how this time works, and that physics is the same.
exactly.
So you can
But
define, so based on that physics, so you can define some quantities that doesn't change with respect to what reference frame you have.
correct.
So these things are fine. So the theory itself is not, so there's nothing wrong. So it's not that my theory for space and time is different from your theory of space and time. There is a theory that is describing how space and time are relative.
Okay.
So there were theories that described how space and time are absolute. But now there is a theory that describes how space and time are relative. And this is how nature is working. Nature is working with respect to, nature is not working in a way where things are absolute. Nature is working in a way where things are relative.
Okay.
And now we have understood how things have become relative. So
Okay.
that is the theory. So that
But
is
the
how it is.
physics is same in all the frames here.
So what do you mean by physics is same? So
Or
the way, the equations
the
that
laws of
govern,
measurement are same whether I am measuring from a train or from outside.
no, right? If you measure time, if you measure time, if you measure time for me is different when compared to a person who is flying in a rocket, right? The
Correct.
time is different, but there is physics that describes how time is different.
Yes.
Earlier, physics described that time has to be the same for me or the person in the rocket. But now nature is not working that way. And physics is now describing how time is different for me and for that person.
Correct. But they say there's an underlying assumption here that for each of that frame, the speed of the time is same. So in fact,
Speed of time, I don't know what speed of time is.
Or the ray. See, the thing is the
Time
speed.
itself is different. There is nothing called a speed of time. Time itself is different.
Oh, so what I've heard, what I have seen is that in the one of the fundamental things with Einstein is he said everything moves at the light moves at the same speed.
That's right. Yes. So in every reference frame, light moves at the same speed. That is correct.
Yeah. So that the physics of that is same in all. That means
So it is right.
So
whereas that
it
can
is-
also change in other.
So the speed of light.
Another way.
So it is because the speed of light is the same in all frames that time is different for different frames.
Correct.
So yeah. So that is the relativity part. So the physics describing is that the speed of light is the same. That is because of that time is different. Yes.
So yeah.
Speed of light being same itself is invalidated because of non-local universe.
So that is not a real thing anymore. So speed of light is the same in this universe is the fact. The non-locality of universe is not a thing actually. So there's a loophole that people haven't thought before, but now it's cracked. So what happens is actually the universe is local. It's not non-local. Information always travels at the speed of light. So it looks like it's non-local when you have these entangled particles. when you have this quantum entanglement. But it turns out that even though they are entangled, the information that they are entangled always goes at the speed of light. So, so if you want to convey this information that things are entangled, that is still limited by the speed of light. In that way, because that information can travel only at the speed of light, the universe is still local. What can expand at speeds greater than light is space. So space can expand at speeds greater than light because there's no information there. But anything that carries information with it or is always limited by speed of light. So that's why this non-locality thing is still not a thing. Yes.
Too confusing.
Yes.
Yeah.
Yes. The only thing that can expand faster than speed of light is just space.
Okay.
Yes.
So any question, Jagdish ji? You have, yeah. Go ahead. Okay. So, okay, thanks, Pranav. If there are no questions, really, it's already 10 o'clock.
I think he's muted.
Oh, sorry. Can somebody unmute Jagdish ji? Yeah, go ahead.
Now you can hear? Yeah.
Yes,
so
yes.
You are explaining that there is space is 3 dimension and time is 1 dimension. It becomes 4 dimensions, something like that.
So you can think of 3 dimensions of space. So we can move in 3 dimensions. We can move along X. We can move along Y. We can go along we can go along X. We can go along Y, and we can go up, which is Z. So these are 3 dimensions of space, and there is 1 dimension of time. So time is always moving forward, right? So now it's 1 second. 1 second later, it becomes 2 seconds, so on. So that is dimension of time. So so earlier it was that space is different, time is different, but now space and time are not different. They are in fact the same things. You can have a unit of length of time depending on the speed of light. I'm sorry, I can't hear.
Yeah, you mean that's a light year? Okay.
What?
Light year is still length, right? What you are saying, a unit of speed of time, or the Planck? What are you saying just now?
Oh, I'm saying you can define length. The way you think about how length of time works, because time is different and space is different. But how time works as space is when you when you consider in units of speed of light.
Okay. Yeah.
Because speed of light is a constant, you can think of it in terms of length. Yes.
That's what you call as Planck length. What is Planck?
No, this is not Planck length. It is still just a unit of length. It's just okay. If I say you travel 60 kilometers per hour, in 1 hour you travel 60 kilometers, right? So I can define unit of time in terms of length that way. If you went at 60 kilometers per hour, if you went for 15 minutes, you would go you would essentially go for 15. You would essentially go 15 kilometers. If you went for 1 hour, you would go 60 kilometers. If you went for 2 hours, you would go 120 kilometers, right? Because 60 kilometers per hour is fixed. So if I change time, you change the distance you cover as well. If I went at one particular speed all the time, then depending on how much time I drive, you go different lengths, you travel different lengths, right? If you go for 1 hour, you go 60 kilometers. If you go for 2 hours, you go 120 kilometers. So similarly, you can think of that the entire universe's speed is fixed at one point, which is speed of light. It's not, this is a very naive explanation. It's not that the universe is moving at this speed, but the the dynamics of the universe is managed by the speed. So then you can define a length for that universe. You can define a length of time scales for that universe. It's just multiplying the speed with the time, and that is how time works as a unit of length. Another dimension, but it's similar. I hope I was able to explain this, because it's a little bit difficult to understand.
Yes, but it's good. Yeah, Jagdishi, you still have a question? Sorry, can you repeat your question, please?
Nothing. I wanted a graphic example, but it's getting late. I don't know whether Pranav has the time to explain.
I can explain.
Yeah.
Yes.
Can the graphic image explain?
A graphic image of what?
Maybe of this speed and time relationship.
Not sir. I'm still in that 3-dimension space and 1-dimension time. I'm audible?
Yes.
Yeah. So that part, can you give another graphic example? You gave the XYZ example.
Yes.
Okay. Now can you create a graphic image around that and explain what happens when that XYZ is fused with time?
Okay, fine. I can show it to you. I can just draw it over here.
Yeah.
Is there a way for me to draw it? Can I? Okay, let me just share my whiteboard.
So whiteboard.
Yes. So let's say there is an object moving. Let's say I throw a ball. So when I throw a ball, let's say I throw it at an angle like this. So what I graph is the position, height, and I draw the distance that the ball covers. So let me put this as R. So let's say I throw the ball along this height, along this way. So what happens initially? Initially, the ball will start rising. So height will increase and distance will also increase. Then it will go to the maximum height, and then the ball will start dropping down, right? So this is how the ball has traveled with respect to height and with respect to distance. So now how has it traveled with respect to time? So let's say this is time and this is height. So as time increases, my ball has gone up. So with respect to height, my ball goes up for a certain time. And then ball starts dropping. So the ball goes down. So this is how my height depends on time. And let's see how my distance R depends on time. So initially it traveled some distance. So with respect to time, what you'll see is that this is how it follows. So it travels at, so this is the path that it takes. So this is how height goes as a function of distance. This is how height as a function of time is. and this is how height as a function of range distances. Sorry, time range as a function of time is. So now you can make a 3D model, right? So these are all 2D graphs. Height as a function of time. Sorry, height as a function of time, height as a function of distance, and distance as a function of time. So now I can make a 3D model. Height as a function of time and distance, right? So it will follow some 3-dimension, it will follow some path over here. So did you follow this one?
Yeah.
Yeah, so this is, so you can combine this graph, and this graph to make a 3-dimensional graph of how the object is moving.
Yeah.
So
Okay.
in this, so this is how, so now this time, so this time is actually a part of this 3-dimensional model, right?
Yes.
So this object was moving in 2 dimensions of space and 1 dimension of time. Now I can
Yes.
combine this and this to create this model of height, time, and space, and the object is moving along with it. I can combine
Yes.
this graph, and this graph to create this 3D graph now.
Yes.
And this is the same way you do for 3D as well, except that I can't sketch it because I need 4 dimensions. Because when you take 3 dimensions of space and 1 dimension of time, it becomes 4 dimensions.
Yeah.
So I can't, there's no easy way for me to draw it.
Yes.
So the entire object moves in 4 dimensions. Just like how this ball moved in 3 dimensions over here, by taking this graph, and this graph, that ball moves in 4 dimensions because it's moving in 3 dimensions of space and 1 dimension.
Yeah. So you are explaining that from the edge you can figure out what is happening inside.
That's
in
right.
this, where is the edge?
So in this one, the edge, edge is nothing but, so for example, edge is nothing but what happens. So let's say this is, so let's say it takes a path over here. So it takes up a path. So if there is an object, so let's say I have a ball here. Let's say I'm looking at a ball. So let's say the object corresponds to a ball over here. So now in order to explain, let's say I want to know the volume of the ball, how much I want to know how much how much volume there is inside the ball. So essentially I want to know if I want to fill this ball with air, how much air I need to put. So one way to do it is I measure how much it has, what is the dimension in X, what is the dimension in Y, what is the dimension in Z, and there is some relationship that X and Y and Z obey because it's forming a ball, right? So X is dependent on Y, Y is dependent on Z in some way because it's forming a ball. So now if I were to find out the volume of the ball, you have this high school formula, 4/3 pi r cube, where r is nothing but the radius of the ball. So if I want to know the volume of the ball, I just need to know the radius of the ball, right? So radius is just one quantity. I don't need to know how X and Y and Z are dependent on each other. The ball is living in 3 dimensions. So it has X, Y, and Z. But because the ball is shaped in some way, I just need to know one quantity, which is this object called radius, in order to know the volume of the ball, right? I don't have to know how much X, at every X, I don't have to know what value of y and z it has, right?
Yes, yes.
So for example, if I take this ball, what I can do is I can cut this ball down into rings. Now this ring will have some area, right? If I take a ball and I keep cutting this ball down, it will have all these different areas, right? Now I can add up all these different areas because and these areas will be different because the height is different, right? But I in fact don't have to do all of these things. All I need to know is I need to know the radius of the ball in order to know the volume of the ball. So this way, because it's a sphere, and because its shape is in that form, I don't have to know all the three things in order to know the volume. I just need to know this one single thing, which is the radius. In a similar way, the universe near a black hole, it has certain properties like this. It's constrained to form certain shapes, certain objects. So in order to know the volume, I don't have to know all the XYZ things. I just need to know two things in that case. I just need to know how it behaves at the boundary. If I know how it behaves at the boundary, I can get information about the edge as well. It's just like let's say I have a cube. If I look at the corners of the cube, it forms a square, right?
Yes, yes.
If I look at if I look at a sphere, then if I do a 2D projection, if I just look at how it, if I just cut a slice of that, let's say I have an apple, I cut a slice of the apple, and if I look at how the slice is, it will look like a circle, right?
Yes.
So if I just look at the circle, I know the 3D object is not going to be a sphere, right?
Yes, yes,
Because it's
yes.
circular. And if I look at the square, I know it's not going to be a sphere because it's square in nature.
Yes.
So the object is some sort of a cube. The object is not a sphere. That much I can tell, right?
Yes.
By
yes.
just looking at how the square is. By just looking at the square, I can say it's not a sphere.
Yes.
By just looking at the circle, I can say it's not a cube.
Yes.
In a similar way, by just looking at the edge of what is happening around, I can comment about what is happening inside the bulk as well.
Yes.
So this is how and because there are certain symmetries, there are only certain ways in which it can be. I can get more and more information by just looking at the 2D, by just looking at what happens in the edge.
Yes. Yeah. Nice.
Okay.
Thanks a lot.
Okay. Thank you,
Thanks.
Pranav.
Yeah. Thank you.
Thanks, everyone. Hari Om.
All right.